First, they told me that I should draw your attention, Nicolas and Goulven, to this school, which seems to be very exciting, because there will be courses about arc spaces, or minimal structure, Berkovich spaces, Hodge ideals, resolution of singularities, and things like this. Vertex algebras, course about every one of these topics. Then it's, I would like to thank the organizers here to give me the honor to speak in honor of Bernard. I think that admiration to Bernard comes here in family, and I am a fiber in this admiration. And he has a lot of influence on my mathematics, but also Bernard is a great friend who has a lot of influence on my person and continues to have a lot of influence of my person. So I'm very happy to talk about Teissier singularities. This is a work with Bernd Schober. And during this talk, K will be an algebraically closed field of, at the beginning, it will be of characteristic 0. And I will be considering a polynomial f in K of x1, xd, z. This is a power series here, z, which is a Weierstrass polynomial. So something like this, f is equal to z to the n plus a1, z to the n minus 1 plus etc. plus an, where f of 0 equals 0 and ai belongs to k of x. And during all the talk, I will consider f to be irreducible in this ring here, irreducible. An important definition for this talk is first that I will say that f is a quasi-ordinary polynomial if the discriminant with respect to z of f is a monomial times a unit in k of x. And then we have a projection which is associated with this morphism here. And I will say that f is, let us call it this pi or pi star, that f is quasi-ordinary with respect to pi if f can be transformed to a quasi-ordinary polynomial up to a change of variables which change of variables of k of x z, which preserves k of x. Okay, so up to automorphism of k of x z, which preserves k of x. Okay? So, yes?
Pointwise?
Point.
It fixes pointwise Kelvin?
I don't really understand the question. This, I would say that this.
Identity, it should be the identity of Kelvin?
No, it should not be the identity. No, it shouldn't be the identity. Okay, not pointwise. So this means that x goes to h of x, and z go to z plus something in x. Okay. And maybe I continue here. Now the singularity or the germ of singularity x0 in this situation will be called quasi-ordinary. So why these singularities are important? Because imagine that we have a surface, because they appear in what one call now the Jungian approach to resolution of singularities. Which goes a bit like this. So imagine that we have a surface. So if I have a surface S, okay, then thanks to the Noether normalization theorem, I have a finite morphism I can project in C2. And here I have the discriminant, which looks like this. Okay, so this is a discriminant here. And we know how to resolve curves. So we make an embedded resolution of the curves, which means transform it to something like this. And then we take the pullback by the resolution morphism. And we will have Z here, which will have only quasi-ordinary singularities. So in some sense, this, which means that every time we have a singularity here, if we look at the completion at this point, we will have a singularity which is like this. So this, in some sense, reduces the problem of resolution of singularities or embedded resolution of singularities to the resolution of singularities of quasi-ordinary singularities, modulo a patching problem that I don't want to talk about. But this approach led to the first proof of resolution of singularities of surfaces by Walker in 1948. And I can also say that this approach allows to study some problem in equisingularity. The good thing is that we know how we have a good understanding of a resolution, somehow, of a resolution of quasi-ordinary singularities, or also of quasi-ordinary singularities, thanks to the following theorem, which is called Abyankar-Jung theorem. Which says that the roots of f belong to k of x to the power 1 over n. N is the exponent of z there, which is equal to k of x1 1 over n, xd 1 over n. Why this theorem is important? Because it allows us to define some invariants. So since we have, if we take the roots, psi1 till psi r, the roots of f, then we know that psi I minus psi j, since it divides the discriminant, which is a monomial, times a unit, is equal to x to power some power lambda ij times a unit uij, okay? And this lambda ij belongs to k to rational to the power d. And you remark that if I take psi I minus psi j, I can also write it as psi I minus psi 1 plus psi 1 minus psi j, okay? So this is equal to x to the power lambda I1 times u I1 plus x to the power lambda 1j times u 1j, okay? And since we know actually that there can no be cancellations because we know the action of the Galois groups on the roots, this tells us that lambda I1 or lambda 1j is equal to lambda ij. So this tells us that the set of lambda ij is actually equal to the set of lambda 1j, okay? We make only j varies, and also that, so if it was equal, let's say, to lambda ij equal to lambda I1, this tells us that x lambda I1 divides x lambda 1j, okay? So this means that these monomials, or the exponents of these monomials, are ordered with respect to the product ordering, okay? So I can say that we can, the lambdas, we can order them with respect to the product ordering. So let me lambda 1, 2, etc. Let's say that there are g of them, lambda g, okay? And this is the product order. Okay, so from this, I have defined this somehow invariant, but let me do some gymnastic with this invariant, which may appear a bit strange. So let me define the lattice M0 to be ZD, and then define Mi to be equal to Mi minus 1 plus Z times lambda I, and to define Ni to be equal to the index Mi minus 1 Mi, and to define some invariance, gamma I, which given by gamma 1 equal to lambda 1, and by gamma I recursively, gamma I minus 1 is, minus Ni minus 1, gamma I minus 1 is equal to lambda I minus lambda I minus 1. So these are just some vectors, and all what I want to say is that the data of the gamma i's is equivalent to the data of the lambda i's. And the good thing about this invariant is that there is a theorem by Gao. I must say maybe that these invariants were introduced by Lippmann, okay, the lambda i's by Lippmann. Ni should be equal to the index of Mi in M minus 1. This is what you wanted to say? Okay, thank you. So what I wanted to say is that the lambda i's, or equivalently the gamma i's, determine the embedded topology of quasi-ordinary singularities, of the singularity. Okay, which means that, well, I can, if I have two singularities, one which is defined by f equals 0 and the other h equals 0 in, let's say, CD plus 1, we have homeomorphism which goes from CD plus 1, 0, CD plus 1, 0, or we can have if you like, an open set here U and V. So U is homeomorph to V, and U intersected with F equals 0 will be sent to V intersected with H equals 0. Okay? So I wasn't, what I wanted to say is that this homomorphism is a homeomorphism from U to V. So there is an homomorphism from U to V, which send F equals 0 to H equals 0, whenever F and H have the same characteristic exponent lambda I. So allow me to define a first target. This is a fantastic thing. Usually we don't have such an invariant, such an easy invariant which determines completely the embedded topology. And one would like to generalize this, maybe to all singularities or to a larger class of singularities. But the problem is that, as you have seen, this invariant lambda i's were defined using the roots. And in general, the roots are much more complicated. So if you try to define invariants using the roots, it will be much more complicated. And if you consider, if you are in characteristic P, then things are much more complicated. Okay, much more complicated, which means, for instance, even if you are in one variables, it took Kedlaya something like 5 papers to resolve, well, just to write, because it's very difficult to write what is effectively what is the algebraic closure, what is the form of the roots, based also on other earlier work. So let me give a first target to determine the gamma i's from the equation, or to determine the lambda i's or the gamma i's from the equation, and also to at the same time to characterize somehow differently quasi-ordinary singularities. So for that, I will define an invariant that I call kappa, which is an invariant of this projection, pi. So let me take kappa of pi. This is an invariant which is have the following form, so V1 till Vg. And the last component is -1 or infinity. And the Vi's belong to Q positive to the power D. And this G will depend on pi or on F. Okay? So for that, I will consider, to begin, I will consider a kind of projected Newton polyhedron. So you have seen Newton polyhedron.
Just a question that theorem is you write the lambda i's equivalently the
gamma i's. Merci beaucoup, Paul Emmanuel. The lambda i's. Okay? So this, let me construct for you this invariant, and it uses at the same time a kind of Newton polyhedron, or a more intrinsic version of a Newton polyhedron, because as Patrick was telling you that Newton polyhedron will depend on the variables. Now we will somehow optimize this Newton polyhedron, and it will use also embedding, changing the embedding, okay, a theme which is very important in the work of Bernard, as also was mentioned by Patrick. So how we define? First, let us write f of this form. So f, we can write f plus sum of x to the power, or let me write like this, x to the power a, z to the power b, and this is the coefficient of ab. So I will consider the projected polyhedron, let's call it delta of f x z. This is the set of a divided by n minus b plus r plus to the d. Whenever, no, sorry, this is the convex hull, whenever the coefficient of the monomial is different from 0. Okay, so this may look something strange, but in fact this is just, we take the Newton polyhedron, and you see that on the Newton polyhedron we have the monomial which correspond to z to the n. So we will project from this point z to the n, and then we will make a dilation by multiplying by 1 over n. Okay? So, but as I said, even this object is very much depending on the variables x and z. So what Hironaka considered is the So trying to make, as I said, this object more intrinsic, he considered delta, which is equal to the intersection over all the automorphisms that I mentioned here. Let us call them odd, as Bernard suggested. Delta of f x z. And the important thing is that Hironaka proved that there exists a system of variables xz such that delta, this one, is equal to delta f x z. Okay? So this, as you remark, this delta minimizes the projected polyhedron with respect to inclusion. Okay, this one is included in all of them. And what we are saying is that, well, there exists a special variable, x and z, such that we have this equality. For instance, let us look at an example. If you take f to be equal z minus x squared minus x cubed. Okay? So now the projected polyhedron is given by this. The Newton polyhedron, if you try to see it, it has 2 points, or not 2 points. This is the Newton polyhedron, and here we have 2, and here we have 2. So what I said is that we will project on the one on the this half line which is downstairs, and then we make a dilation by 1 over 2. So what we obtain is something like this. So this is 0, infinity, and this will be the Newton polyhedron. Okay? But now, if I make a change of variable, I can make a change of variable. Instead of z, I take z equals z minus x. I change, sorry for keeping z. I change z to z minus x. Okay? So this, then the transform of f, that I will call again f, very bad idea, but still, then it is like this, z2 minus x cubed. And then if I play the same game, I see that actually the projected polyhedron looks like this. 3 over 2 till infinity, okay? So as you see, this polyhedron is included in this polyhedron. And actually, I cannot minimize it more, okay? So this is the maybe I can say that Hironaka only considered this with respect to variables in Z. So as Francois said, he fixed X, okay? So, but we added this transformation, which is important for us. So now we are ready to determine the first component of kappa. There are three possibilities. Either this delta has only one vertex, V1. Okay, so it's something like this. Either it has, it is empty. Either it is has more than one vertex. More than one vertex. So in this case, I will put that in this case, kappa of pi is V1, and I need to determine the others. In this case, I'm already done, and I know that kappa of pi is equal to infinity. And in this case, I also am done. Kappa of pi is equal to -1. Okay? So if the interested case for me now is V1, because in this case, I didn't determine yet the invariant kappa. So in this case, as we said, we have only one vertex. Okay, so it looks like this. And I will take all the monomials in F which projects on this point. Okay, so I will consider the initial form with respect to V1 of F, which is by definition Z to the n plus sum. Whenever I have that this monomial, a monomial in F, projects on V1, I put this in, okay, in this polynomial. And now, what happens is that one should imagine that we had our Newton polyhedron, and now we are considering all points which are on a segment, okay? So this is a polynomial whose monomials are on a segment, and actually we can transform this monomial to a monomial this polynomial to a polynomial in one variable, which is, this variable is given somehow by the directing vector, primitive directing vector of this segment, okay? So we can transform it to only one, to a polynomial in one variable. And since I consider that K is algebraically closed, it can be written as a product of binomials, okay? And to some power, of course. And thanks to Pedro Gonzalez Perez and Ebelia Garcia Barroso, we know that since I consider that it is irreducible, I can have only one binomial to some power. That is, I can write it as Z to some power n1 minus x to the power a1, all of it to some power, there is a coefficient here, okay? All of it to some power, which is called e1, okay? And of course, as Francois remarks, this n1 has a very particular property, is that this n1 is larger strictly than 1, right? Everybody agrees? It is strictly larger than 1. Damien, you agree? Damien agree. Why? Because otherwise, if imagine that n1 is equal to 1, then I can make the change of variables z go to z minus what is here, and this makes the polyhedron smaller. Okay, I can make this change of variables, and in some sense, if I do this, I will be deleting this vertex, okay? Because we have this projection here. This is what we are seeing somehow. So when I'm making this change of variable, I'm pushing somehow this polyhedron, okay? So a very important information here that we have, that n is equal to n1 times e1, okay? And that this n1 is strictly larger than 1. So what I will do now, something very much inspired by Bernard, he does this all the time. I will consider a variable, let us call it u1, which is equal to z to the power n1 minus some coefficients times x to the power a1, okay? And I will consider a transform of the polynomial f1. So let f1 be the polynomial which is obtained from f by changing or by substituting there is a t here, z to the power n1 by u plus some coefficients times x to the power a1. So this tells us, u1, this tells us in particular that f1 belongs to k of x, and I have the variable z, but which has a degree less than n1, okay? And then u1, okay? Because whenever I have seen z to the power n1, I have changed and introduced u1 instead, okay? So all the variables z appearing in f1 are smaller than n1. And now I play a game which is somehow similar to the game that I played before, which is I will consider a kind of weighted projective polyhedron. So this is delta of f x z u1, f1, sorry. And this will be, let me write first f1, so we can write it as u1 to the power e1. This is the same e1 which is here, plus sum of x, some coefficients, times x to the power a, z to the power b, u1 to the power c. So now this z, I will give it the weight v1 that has appeared there, okay? So this is the same thing as the set of a plus b v1 divided by e1 minus c, whenever I have that the coefficient a, b is different from 0. And of course, I forgot many things, like the fact that I will add here r positive to the d, okay? And here I would like to consider the convex hull, okay? And let me cheat a bit here. So I will consider three cases. One which there is that, let's say delta, this delta here, delta f1 x z u1 has one vertex, u1. Here it is empty, and here it has
more than one vertex. Okay? So as you guess, in this case, I have kappa of pi is equal to V1, and the second and last component is -1. In this case, it is kappa of pi is V1, and the second and last component is infinity. So let me put myself here now. In this case, imagine that we have only one vertex that we will call V2, okay? Then I consider the initial with respect to V2 of F1. So this is equal to U1 to the power E1 plus sum of some A, B, C of, let me write it like this, A plus B V1 over E1 minus C, Z X to the A, Z to the B, U1 to the C. Okay? So, unfortunately, this is not in general a product of binomials. This is the same thing somehow in spirit. It's on a line, but it's not on a line anymore. But what happens is, thanks to we should not forget that we have already a relation. Okay, so let's call this a star. So this is U1 to the power N2 minus some coefficient times X to the A2 Z to the, let's say B2 to the C. So it's to the power E2. Sorry, E2. So it is not in general like this, but this is true up to the relation star. Okay? Right? And now, Francois, N2 is, the very important property of N2 is, Damien? Yeah? The very important property that N2 is greater than 1 is not achieved in principle, unfortunately, because I didn't minimize here, you see? I just considered it and I didn't minimize. So it might happen that N2 if equals 1. If N2 is not equal 1, I stop here. But imagine that N2 is equal to 1. If N2 is equal to 1, so let me write somewhere new. What will happen if N2 is equal to 1? Can anyone tell me what I will do? What I should do? Bernard was laughing, he knows. What do you say? Fantastic. So if N2 is equal to 1, so we can make the change of variables, U1 equal to U1, so to the power N2, which is 1, it's not N2, minus X to the power A2 times Z to the power B2, okay? And then I play the same game. And I will find another N2. This N2 can be, unfortunately, again 1. And I can continue this game. This will continue, and what I should have in mind that I have this. So I had here the first V2, but I had to make a change of variables, so I found another one just here. So this should be the right V2. But then I found that, again, the corresponding N2 is equal to 1, so I can continue, okay? So I can have a series here. If I stop, I'm happy. But it happens that I can have a series here, right? But the good thing is what? Is we should remember something about the coefficient of Z here, the exponent of Z, is that it is smaller than N1, okay? So the coefficient of Z should be small, but the weight of this monomial is growing. This obliges the weight of X to grow. Okay, so this obliges the exponent of x to grow. Since the exponent of x is growing here, what I'm considering here, it will grow and grow, and actually I am considering a series which will converge for the x-adic topology. So what I've just proved to you is that we have actually a kind of a weighted characteristic polyhedron, so that there exist variables x, z, u1, such that delta of f1 x z u1 is minimal for inclusion, is minimal for inclusion. Okay? So I take this one, and now I tell you that there are three possibilities. Either it has one vertex, this is the V2, the seeked V2, the one we're searching for. Either it is empty, either it has more than one vertex. So we are interested, of course, in the case where it has only one vertex, which we will call V2. In this case, I will consider the initial form, V2, with respect to F1, and now it will be something, modulo the equation there, it will something of the type U1, the seeked U1, the one I found here by considering this transformation here, it will be U1 to the power N2 minus X to the power A2 times Z to the power P2, all of it to the sum to the power E2. And now, Francois, what I can say about N2? Now N2 is obliged to be greater than 1, okay? So what I remember here that we had that N was equal to N1 times E1, and N1 was obliged to be larger than 1, so this means that N is larger than E1, and then here we have that E1 is equal N2 times E2, and N2 is larger than 1, so this means that E2 is smaller than E1, and I have a decreasing sequence of positive integers, and this should stop, okay? So this tells us that, I hope that I convinced you that we have constructed an invariant kappa which look of the type that we have just said. It's just look like this. Let me tell you how. Kappa of pi is equal to V1 till Vg, and the last component is either -1 or infinity, okay? So if it is infinity, means that we have got till the end and we have obtained an empty polyhedron. So let me announce, maybe now not announce, but let me say this theorem. So this was Bernd. We have proved that the last component of kappa of pi is infinity if and only if x0 or pi, if you like, with respect to pi, is quasi-ordinary. Moreover, we have achieved the target that you weren't convinced of, maybe, which is there, which is to determine the lambda i's from the equation. Actually, the gamma i's are exactly the vi's. Okay? But now, actually, we were very lucky, as usual. In my case, for instance, being at 2 places from Bernard's office. So now also we were very lucky because this theorem is false in positive characteristics. Let me give you an example. If you take P equal 2, and if you take F to be equal Z squared minus X1, you can take the plus, X2 times Z plus x1 cubed x2 plus x1 x2 cubed. Then if you consider the first, you see the first projected polyhedron, it looks like this. So here I have the point 3 over 2. No, it's 1, 3 over 2. Here I have the point 1, 1, and here I have the point 3 over 2, 1. And actually, I cannot minimize. This is already the characteristic polyhedron. And I guess that you are able to compute the discriminant of this one with respect to z. So what is the discriminant of this one with respect to z in characteristic 2? If you compute like delta equal b2 minus 4ac, you find that it is the discriminant with respect to z of f is equal minus x1 x2 square, or x1 x2 square. Okay? So it is quasi-ordinary. But as you see, kappa of pi is minus 1. Okay? Kappa of pi is directly, or kappa of f, allow me to abuse of notation, kappa of f is actually equal to minus 1. Right? Okay? Because the first characteristic polyhedron has more than one vertex. And actually, I can show you also that, let me, before that, give a definition, an important definition, eloquent definition. Sorry, I should not erase. If you imagine that you have something like this, z to the n1 minus x to the a1, and other things which are inside, okay? Then you will make a change of variables, u1 equals z minus 1, etc., and you end up having as a function u1, okay? And since we are, okay, so then it will empty. Okay, so good question. And this allows us to give the following definition. That we will say that x0, again defined by f. So we are, again, remember that we have k is algebraically closed, has a Teissier singularity if and only if the last component of kappa, pi, is infinity. As I showed you there, you can be quasi-ordinary but not Teissier. And you can be Teissier but not quasi-ordinary singularity. So you say to me, but why do you want to have something which is other than quasi-ordinary singularities? Because in the Jungian approach to resolution of singularities, you first reduce the problem of resolution of singularities to the resolution of singularities of quasi-ordinary singularities. This is good in characteristic 0, but in positive characteristic, this is almost as non-reducing it. For instance, Cossard and Piltin resolve singularities in dimension 3 in 300 pages. 20 of them reduce to the case of quasi-ordinary singularity, and then 280 to resolve quasi-ordinary singularities. So resolving quasi-ordinary singularities in positive characteristic is almost as difficult as resolving singularities in general. And actually, maybe Abyankar was trying to lead this approach in positive characteristic, and this led him in very simple cases already to introduce what's called Abyankar conjectures. So things are very difficult. So we would like to replace, in some sense, these singularities by new singularities. Now, as I said, Teissier singularities in characteristic 0 are the same thing as quasi-ordinary singularities. in positive characteristics, why I am pretending that this is a good analog of quasi-ordinary singularities, because we have the following theorem, which says that a Teissier singularity x0 is the special fiber of a family so let me write here over spec O, and since I considered K to be algebraically closed, it is in particularly perfect, so I have a discrete valuation ring of mixed characteristic such that whose residue field is K, okay? So let's take O, so this is, if you think of K to be equal FP bar, then my discrete value ring is OCP, okay? So I have a one parameter family, okay? Is a special fiber of a family X spec O whose generic fibers are quasi-ordinary. Of course, the generic fiber are in characteristic 0 because this is mixed characteristic, are quasi-ordinary. Now, this is not the important thing. The important thing is that this family, the family X, is equisingular. What does it mean, equisingular? Equisingular means that there exists an embedded resolution in family, something that Bernard used to do all the time, continue to do all the time. So there exists an embedded resolution in family of this. In particular, this resolve Teissier singularities. Now you will say to me, but if you have arrived to resolve these singularities, this means that these singularities are easy to resolve. Well, maybe, but from the viewpoint of resolution of singularities, if you come to resolve these singularities from using, for instance, the classical approach, Hironaka's approach, or its development in positive characteristic, these are difficult to resolve. But when we do this deformation, there are some monomials that we call ghost monomials that appear in characteristic 0 and that we cannot see in positive characteristic. And when we see them in characteristic 0, this allows to resolve the generic fiber, and resolving the generic fiber, we resolve the special fiber. I maybe should say that the generic fiber, as I said, is a quasi-ordinary singularities and can be resolved by toric morphism. This is what Pedro González Perez has done in his PhD thesis with Bernard. Last thing that maybe Francois will allow me to say is that this is also the fact that we call them Teissier singularities. There are many reasons. First of all, I never remember why we have called them quasi-ordinary. So I said, well, this is a good thing. We have a characterization. We get rid of quasi-ordinary singularity. An important one is that we love Bernard, Bernd Schober and myself. But maybe a very good reason, another very good reason, well, the middle reason is the best one, but another very important reason is something that also was mentioned briefly by Francois, which is that we proved with Bernard and Kutkowski that if we are in the situation where we are similar to what we have here, we can consider monomial valuation over K of x, and we can look to the lift valuation or the extension of valuation to k of x z over f. And what we were able to prove, not in the moderate cases, which means in the case where p doesn't divide n, is that this is a quasi-ordinary singularities if and only if the graded algebra of the extension of the valuation varies in some sense uniformly. So actually, the graded algebra does not vary that much. It's just the weights of this graded algebra which varies. So if it is like this, this is a if and only if information about quasi-ordinary singularities. But the important thing is that this graded algebra has a shape. Well, Bernard, in the case of Abyankar valuations, represent the graded algebra as an overweight deformation of some toric variety. And in some sense, these Teissier singularities, in some sense that we didn't prove yet, are like, we have this feature of this of Abyankar valuation, we have this features, we have this overweight deformation, but globally, not only for given Abyankar valuation. And let me thank you again for the organizer for giving me this opportunity to speak in honor of Bernard. Thank you very much.
Thank you so much.